Well, welcome everybody.
Yes. Welcome indeed. Thank you all for joining this webinar about serial communication technologies and methods and things like that. My name is Clemens Valens. I work for Elektor, and I will be co-presenting this webinar with my colleague Brian Williams. Brian will be answering all the difficult questions. Hi Brian, how are things in South Africa today?
Great, thank you. We're having a bit of challenge with power issues as usual, but I'm here with my battery backup, and I was quite excited to be joining this because I've been playing with serial buses for years, even bit banging on occasion back in the day. But you've been doing this stuff for longer than I have. When I started with buses, it was parallel because that was easier. But then I eventually learned serial. How did you first get into these buses?
Me? Well, because of work, I suppose. I had to use
parallel
it.
Serial. Parallel or serial?
Well, first we started with parallel and then moved on to serial, like you say.
Yes, and we do have the same libraries as one of the viewers noted.
Yeah, indeed. This webinar is intended for people interested in serial communication technologies, and we will discuss some popular techniques. But as it is a vast subject, it will not be possible to detail everything in full detail. But first, some announcements. So, as you can see, this webinar is brought to you by Elektor. In case you don't know Elektor, it is a platform for electronics enthusiasts and professionals. Elektor publishes websites, books and magazines and videos about electronics. And you too can contribute to Elektor by either posting projects at the Elektor Labs website or by filling in the proposition form. Maybe you can put a link in the chat so that people know where they can post their proposals. Second announcement is that there will be a giveaway, which is this book. I have it here. Embedded in Embedded. Why is this now activated anyway? Embedded in Embedded. At the end of the webinar, we will give away 5 of these books. It's a very thick book, more than 500 pages, and it's all about embedded programming and stuff like that. So if you have a question, you can probably find the answer in this book. Let's see. Oh, yes. This presentation is pre-recorded video of about 30 minutes. And after it, we will do a Q&A session. And then you can type questions in the Q&A chat box, which is below. It's on the right for me. So, and don't worry if you can't follow along with the presentation. It is being recorded and will be posted on our YouTube channel afterwards for a replay. So I think we can get started now, Brian. Don't you think so?
Yes, indeed. We've got people from all over the world, which is quite exciting. And I'll keep an eye on your questions, and then we'll address them after the pre-recorded video.
Okay, then I will launch the video. Serial communication methods are used in all sorts of applications. Machines, tools, and instruments can communicate over serial connections. Household appliances do too. And some of the ICs inside the device use serial communication. Because there are so many applications for it, there are also many ways to do serial communication. In this presentation, I will show a few of them and explain the underlying principles. At the end, I hope you will have a better understanding of serial communication that enables you to choose the method that is most suitable for your application. So, what exactly is serial? A good start with these kind of questions is to look in the dictionary. There we find that serial data transfer refers to the process of sending data sequentially. Sequentially means one after the other. Therefore, serial data transfer or communication is transferring one piece of data after the other. Actually, communication is not a good word, as it implies some sort of dialogue. The data transfer methods that we will be looking at are often one-way, especially at the wire level. But as communication is such a common term in this domain, I will use it too. Now, why would you want to communicate serially? Simply because the amount of information that you want to transfer through a channel is too big to go through that channel in one go. A channel in our context is one or more wires or PCB traces. To increase the data throughput, you can try to increase the data transfer speed, or you can put several channels in parallel. Higher transfer speeds require faster components, and increasing the number of channels demands for more circuit board space and components with more connection pins. Like everything, it is a compromise between costs and importance. The fact that we say serial communication and not just communication implies that there are also other forms of communication. That is correct. There is exactly one other communication form, and that is parallel communication. In pure parallel communication, all the data is transferred at once. Parallel communication requires a wide channel or many wires. If the data fits into 1 byte, 8 wires are needed. If the data consists of 128 bits, then 128 wires are needed. Microcontrollers usually use parallel communication internally. They can have buses that are up to 64 bits wide or more. A simple calculation like the addition of two 32-bit numbers A and B can be done with parallel communication. Fetch A somewhere from memory, then fetch B, do the addition and store the result somewhere. This requires 3 parallel data transfers. Parallel communication usually connects more than 2 devices and therefore adopts a bus structure. The bus typically has one master and several slave devices. The master decides when and what to do, a read or a write, and which slave device is to be involved. Data can travel in only one direction at a time, so the bus is half duplex. On this kind of bus, every data word is equal. The bus does not impose any interpretation of the data contents. There is no protocol that imposes a particular order of data words. The signal levels are asymmetric, with a low level being 0 volts and a high level being 1.8 volt, 3.3 volts or 5 volts or some other value. Here is an example of a timing diagram of a parallel bus. Data represents the data bus and its width can be anything. The other signals are control signals: chip select, write and read. If the master wants to send data to a slave, it selects the slave by activating the slave's chip select pin. Then it puts the data on the bus and pulses the write line. When write goes high, the slave knows that the data is valid and it can read it. The master allows a certain amount of time for the slave to do this. When this delay expires, the master makes write low again. If the master wants to read data from a slave, it again first selects the slave. Then it makes the read line high so the slave knows that it must put data on the bus. The master allows a certain amount of time for the slave to do this. When this delay expires, the master reads the data and makes read low again. Of course, there are many variations on the parallel bus theme, but they are outside the scope of this presentation. The reason to move from parallel to serial communication is usually a costs thing. Serial is cheaper. Fewer wires, fewer pins, but it requires converters to turn parallel data into serial and vice versa. Serial doesn't necessarily mean 1 bit at a time, but usually it is. Serial video data transfer methods like HDMI and DVI can use multiple channels. Also, the well-known 4-bit LCD interface can be considered a serial connection. And even in 8-bit mode, each communication consists of a few bytes sent one after the other. Every form of communication is serial in some way. Pure parallel is the exception. It is a bit like a true and false in programming. False is often defined as 0 and true as not false, meaning everything else not equal to 0. Similarly, serial is not parallel. We will stick to single-bit serial communication in this presentation. Basically, a serial communication system needs the same signals as a parallel communication system. The sender must be able to select the destination, and it must tell the destination if it is going to send data or if it wants to read some instead. Therefore, it is not enough to simply convert the data from parallel to serial. The control signals must be handled too. There are several ways to do this, which explains why there exists more than one serial communication method. The chip select signal can remain, as done by SPI, or it can be turned into an address, as in I²C. Another option is to remove the chip select signal altogether, for instance in case of a single destination, a point-to-point connection like a USB, or when you sort of don't care. This is done in, for instance, RS-232, where a sender can have more than one listener, a so-called multi-drop system. You can also move the chip select signal up a level into the communication protocol, as in, for instance, TCP/IP over Ethernet. The read and write signals also need to be converted. Providing separate channels for reading and writing is a solution. The advantage is a full duplex connection where reading and writing can take place at the same time. The main inconvenience is its two channels, one for reading and one for writing. SPI and RS-422 are examples. Moving to half duplex is another way to solve the read-write problem. In such a system, only one node is allowed to speak at any time. Again, there is more than one way to achieve this. For instance, a master can issue a read or write command, as in USB, or the node that wants to send can check first if the bus is free and then take control over it. The CAN bus works like this. Finally, there is a synchronization between the sender and the receiver. In the example of the parallel bus we saw earlier, this was handled by the master with time delays. These delays are derived from the master's clock. In such a system, it is up to the designer to ensure that all the connected devices can handle the required data setup and hold times. This technique can also be used in serial communication systems. The one-wire bus works a bit like this. RS-232 works in a similar way, except that in such a system each node is told what the bus speed is. Then, to respect this speed, each node is given its own clock. Special bits are used to signal the beginning and end of a transfer. Providing a separate clock signal is another solution, especially when data transfer speeds must be high. SPI, I²C and I²S are examples. Besides the synchronization signals, there may be other reasons to do things in a certain way. Altogether, this explains why there are so many methods. This slide lists a few, but there are many more. Before choosing a serial communication method, there are a few things to consider. In many cases, the method is simply imposed by the other party, the peer or the slave or whatever you like to call it. But in case you have the freedom of choice, you must choose wisely. There are several parameters to take into account. In random order, there is first a topology. Who is supposed to talk to who? A master with several slaves? More than one master? Or is every device on the same level? Is everybody allowed to talk at the same time? Or is half duplex good enough? An important parameter is the distance between the participants. The closer they are together, the easier it is, and transfer speeds can be high. On the other hand, when they are several meters or hundreds of meters or even more apart, things become complicated. Then you must deal with cable reflections and interference and all sorts of other problems. Achieving high speeds in such environments requires special measures. Similarly, if there is a lot of data to transfer, you probably want a high-speed connection. But then the distance can become a problem. Data speed and quantity and distance need a compromise of some sort. Finally, for some reason, you may want to roll your own method, because it is cheaper and compatibility is not an issue, or, on the other hand, you don't want to be compatible to prevent people from hacking into your system. Whatever the reason, you may want to consider it. So, after this long introduction, let's have a closer look at the most popular or common serial communication methods. There used to be a time when serial more or less implied RS-232, but that era ended with the appearance of USB to serial converters. Today, serial is a scheme of its own, sometimes also referred to as UART. UART stands for Universal Asynchronous Receiver Transmitter, and it is the name of the peripheral inside the microcontroller that takes care of asynchronous serial communications. I will use it here to avoid confusion with the global theme of this presentation. It is asynchronous because there are no timing dependencies between the devices on a UART connection. Each device has its own clock and runs at its own speed. This is why in UART communication the devices must agree on a data transfer speed or baud rate. They must also agree on the number of data bits in a data packet and what kind of control bits are included. There is no imposed protocol beyond that. A UART link is a point-to-point connection, but there can be more than one listener, which is why it is also called a multi-drop link. Every receiver is a data drop-off place. The link can be full duplex with a separate transmit and receive line, but often it is just a one-way two-wire connection. If it is full duplex and multi-drop, then only one of the receivers is allowed to talk back. The UART signal levels are asymmetric, with a low level being 0 volts and the high level being 1.8 volts, 3.3 volts or 5 volts or some other value. UART style serial is usable over short distances, say up to 1 meter, and speeds can be high. I put 10 megabits per second here to give an idea. The maximum speed is, as usual, limited by the slowest device. My favorite baud rate is 115,200. Here is a timing diagram for a UART style full duplex serial connection. This requires 3 wires. As you can see, the TX and RX signals are not synchronized, but use the same timing for the bits. Note the polarity of the signals. They are inverted. The logic 1 is low and the logic 0 is high. This is common and due to the underlying RS-232 standard that uses inverted logic. Some microcontrollers allow inverting the bit stream, so make sure both ends of the link use the same polarity. A transmission always starts with a start bit. This allows the receiver to synchronize to the bit stream that follows. The receiver will then try to sample every bit right in the middle. This is always an approximation, as its baud rate will not be exactly the same as that of the transmitter, but as long as the speed is not too high, this is not a problem. The receiver resynchronizes on every start bit so the error does not accumulate. This means that for a given baud rate with a 10-bit frame consisting of 1 start bit, 8 data bits, no parity and 1 stop bit, the error margin is about 6%. The shorter the frame, the larger the error margin. So if the transmitter runs at 9600 baud, then the receiver must be in the range from approximately 9000 baud to 10,000 baud. The data bits are ordered as least significant bit first, LSB first, where B means bit. So in this slide, the TX line carries the hexadecimal value A6, assuming there are 8 data bits. In the case of 7 data bits, the value is 26 hexadecimal. In this case, the last bit before the stop bit is the parity bit. Here it is a 1, which means that the parity is even. The reason for this is that with this bit, the count of the ones in the frame becomes 4, which is even. The stop bit doesn't count for parity, neither does the start bit, as it is always 0. The stop bit ensures spacing of 2 frames so that a new start bit can always be detected. If you look at the signal with an oscilloscope, you can determine the baud rate by measuring the length of a bit. Interpreting the bits can be a bit tricky, but as it is most of the time 8 data bits without parity, you can usually make a good guess. As I said earlier, RS-232 is at the basis of UART serial and therefore has most of the same properties. There are a few differences though, the most important one being the signal levels. In RS-232 these are symmetric around 0. A logic 1, also called a mark, is represented by a negative voltage in the range from -3 volts to -15 volts. A logic 0, also called a space, is represented by a positive voltage in the range from +3 volts to +15 volts. Such high voltages allow for long cables that introduce voltage drop. Also, there is quite a large noise margin of ±3 volts. RS-232 was designed for robust data transmission in complicated environments. It allows distances of up to 15 meters and data rates of up to 1 megabits per second, but you will find it hard to get that rate over 15 meters. Looking with an oscilloscope at a real RS-232 signal, you might notice the not so steep edges. This is by design and serves to keep harmonic content low and with that radiation. It is called slew rate limiting. Due to this technique, measuring the baud rate is slightly more complicated. Its definition is the same as before, but the edges are less sharp. RS422 improves on the robustness of RS232 to extend its range to up to more than 1 kilometer. This is done by doubling the TX and RX wires and using balanced or differential signaling instead of unbalanced. Balanced means that the same signal is sent on two wires, but with opposite polarity. This provides for better common mode interference rejection. The receiver subtracts the signals on the two wires from each other. This will cancel everything that has the same polarity on both wires, the so-called common mode interference. The signal, on the other hand, is recovered because it has different polarities on each wire. The price to pay is extra wires. Another popular variant of RS232 is RS485. It is similar to RS422 with balanced signaling, except that it allows for networking. Every node is allowed to send. It is a half-duplex network over two wires. However, there is no predefined mechanism for deciding who is allowed to send at what moment. This must be handled on a higher protocol level. The Serial Peripheral Interface, or SPI, introduced by Motorola many years ago, is somewhat the opposite of UART-style serial. SPI is designed for fast and large data transfers, not for sending small data packets over great distances in a robust way. This is why you find SPI in memory and display applications, even though there are many sensors that do SPI too. SPI is a synchronous system where a master provides a clock signal for every node on the bus. So every budding is running at the same speed as the master. Note that the clock frequency is not necessarily fixed, and it doesn't even have to be stable, as the data sampling points are determined by the edges in the clock signal. There aren't any real timing requirements. This makes SPI a very easy protocol to implement in software. The only thing that the sender and the receiver must agree on is the number of bits per data frame and which edge of the clock signal is important. More on that in a minute. There is no need for start and stop bits, as the slave simply does what the master tells him to do. This implies that all devices on the bus must be initialized in the same way. There is no mechanism to restore synchronization. Like UART serial, SPI 2 can be full duplex, but unlike UART serial, the device talking back to the master is the same slave. This is because in SPI the master must select the slave that it wants to talk to, and only one can be selected at any time. It uses the slave select signal for this. Therefore, only the selected slave can send data to the master. The slave select signal can be a source of confusion, as the master too has a slave select pin and an option to enable it. The role of this pin is not to provide a slave select signal to the slave, even though it can be used for that, but to use the microcontroller as a SPI slave. If you enable this pin in slave select mode, then the microcontroller becomes a slave and will no longer work as a master. On the other hand, if you thought that a SPI peripheral in master mode will automatically use the slave select pin, then you are mistaken. In master mode, this pin is not used because there may be more than one slave in the system, each one requiring its own slave select signal. So if your SPI master isn't working, check how its slave select pin is being used. Like UART serial, SPI uses the same kind of asymmetric signaling. The maximum speed is usually half the MCU's clock speed, but this is not a rule. In practice, the SPI bus tends to run at the highest speed allowed by the rest of the system. Once more, compared to UART serial, full duplex is different, as both the inbound and outbound data must occur during the same clock burst. Therefore, the MISO and MOSI signals must be well lined up. MOSI stands for master out slave in, while MISO means master in slave out. This naming scheme tries to avoid confusion. MOSI always connects to MOSI and MISO to MISO, whereas in UART serial one always wonders if TX should connect to the other's RX or to TX. The bit order on the wire is undefined and can be either MSB first or LSB first, a source of confusion. The slave select signal activates the slave. It might be used by the slave to quickly reset its SPI logic, but in many simple point-to-point systems the slave select signal is tied to ground to save a wire. The SCK slave clock signal is generated by the master. One of its edges, rising or falling, is used to validate the in- and outgoing data. This is another source of confusion in SPI communications. Which edge? This brings us to SPI modes. There are 4, simply numbered from 0 to 3, and they are the main reason why your SPI bus doesn't work. The modes are defined by the idle level of the SEK signal and by the active edge. The idle mode is called C-pole from polarity. C-pole equals 0 when the idle level of SEK is 0, and C-pole equals 1 otherwise. The active edge is called C-phase from phase. When C-phase is 0, the rising edge is used. When C-phase equals 1, it is the falling edge. If the master and slave are not on the same C-pole C-phase combination, there will be trouble. Therefore, always check which SPI mode you must use. But note that there is another, more subtle problem. I did not draw the slave select signal, as it is often not used. Now look closely at the modes 0 and 3. In absence of a slave select signal, how does the slave know that it is supposed to prepare its meso signal? It doesn't. The result is that the first bit read by the master is invalid. Therefore, when slave select is not used, it is recommended to use SPI modes 1 or 2 only and stay away from modes 0 and 3. Developed by Philips in the late 70s, early 80s, the inter-circuit bus, better known as I²C, has become immensely popular. Its reason of being was the desire of Philips to simplify their color TV designs. As the ICs used in them became more complex and produced and consumed more data, Philips needed an efficient way to transfer data between them. At the time, Philips manufactured everything, from the color TV ICs to the color TVs that used the ICs. And so the Philips engineers did what they wanted and protected it with patents. For many years, I²C slumbered a bit until its patent expired at the beginning of the new millennium and it became public domain technology. Note that I got this last bit from ChatGPT, so it may be wrong. Anyway, the fact is that today I²C has become a major player in the serial communication bus field. Like SPI, I²C is a synchronous bus where the master generates a clock signal called SCL for the slave devices. However, unlike SPI, there may be more than one master on the bus. Similar to RS-232-like systems, the bits in the data stream have predefined roles. In I²C, however, data is always sent in 8-bit packets, so the granularity on the bus is 8 bits. However, the most important difference between I²C and the systems discussed previously is that I²C defines a communication protocol on the bit level. If the protocol is not respected, the bus won't work. The protocol specifies several types of transactions, which makes writing an I²C driver a challenge. Luckily, in many cases you can get away with a basic driver implementation. The I²C bus is half duplex. There is only one data line called SDA. I²C also allows multiple masters to share this data line. Therefore, bus arbitration is required to prevent devices from messing up the bus by talking at the same time. This is another source of problems. Instead of chip select signals, I²C uses addressing. Each slave device on the bus must have a unique address. Standard I²C uses 7-bit addresses, which limits the number of slaves to 127. If you need more, you could try to switch to 10-bit addressing, but this is rarely implemented on slave devices. Addressing introduces two types of problems. The first is that the 7-bit addresses are often specified by manufacturers as an 8-bit value, as they append a bit on the right. The reason for this is that the 7-bit address is packed in an 8-bit word, where the 8th bit is the read-write bit. Interpretation of the address therefore can be confusing. Another issue is the fact that slave devices come with hardwired addresses inside. As the I²C address space has room for only 127 values, address conflicts can therefore arise easily. To increase flexibility, many devices feature 1, 2 or 3 pins for selecting another address. 3 pins allow for 8 values only, so even with this flexibility feature, connecting more than 8 identical devices to the bus is complicated. And there is no guarantee that there isn't another device already in the same address space. However, I²C is an excellent solution for simple systems with only a few devices on the bus. Signal levels are asymmetric, like SPI and UART serial. However, I²C is often used with level shifters, so the logic high level can be different on different parts of the bus. Another difference is that I²C uses open drain connections. This means that when all nodes, including the master, are idle, the I²C bus lines can be considered disconnected and floating. They do not carry a well-defined voltage. For this reason, the I²C bus needs pull-up resistors. This is another source of I²C headache and confusion, especially in systems that are made up of breakout boards and other pre-assembled modules. If none of them has the pull-ups mounted, the bus won't work. On the other hand, when they all come with pull-ups, then the bus may not work either, as the total value of the pull-ups may be too low. Speed-wise, there has been some evolution since the introduction of I²C. Originally, it was a 100 kHz bus only. Quickly, a 400 kHz fast mode was added. A few years later, high-speed mode was added that runs at 3.4 megabits per second. There is also a 1 megabit per second mode, fast mode plus, and finally ultra-fast mode at 5 megabits per second. The signals on the SDA and SCL wires look similar to SPI, except that there is only one data line, SDA, and no slave select. However, in I²C, the bits have predefined roles. Also, the order in which the SDA and SCL signals change with respect to each other has become important. The frame shown here is an address frame, the first frame of an I²C transaction. A data frame looks identical, except that the read-write bit is replaced by the 8th data bit. The bit order is most significant bit first, so the hexadecimal value transmitted here is 56. This is a 7-bit address. If a datasheet says that the I²C address is AD or AC, then it includes the read-write bit, and you must shift it right one position. The 7-bit address is followed by the read-write bit. If it is low, then the master wants to write something. If it is high, then the master wants to read something. The ACK or acknowledge bit is special because it's not sent by the master, but inserted by the slave. After sending the read-write bit or the 8th data bit, the master disconnects itself from the SDA line. Now the slave is supposed to send an acknowledge bit. It does this by pulling the SDA line low. For an address packet, this tells the master that the slave has recognized his address. For a data packet, things are a bit more complex. If the master is sending data to the slave, the acknowledge bit is controlled by the slave to indicate that it received the data. If the master is reading data, then the slave is sending the data bits, and so it's up to the master to acknowledge reception. When the master has read all the data it wanted, it sends a not ACK bit or NACK instead of an ACK. This tells the slave to release the SDA line. The clock or SCL signal also has some special features. Most of the time during a transaction, when SCL is high, the SDA signal must not change. If it does change, then the I²C bus logic interprets it as a special condition. This allows the bus to indicate the beginning and end of transactions. A so-called start condition is indicated by SDA going low when SCL is high. The stop condition is signaled by SDA going high when SCL is high too. This mechanism allows for a slave to synchronize to the master. There exists also a repeated start condition that allows the master to keep control of the bus in case it needs to change the data direction. Changing from read to write mode or vice versa requires sending the address frame again, as the read-write bit is only in that frame. Inserting a start condition sequence allows doing this without having to send a stop condition, with the risk of losing the bus to another master. There can only be one stop condition in an I²C transaction. Finally, the SCL signal can be used by the slave to pause the master. This is called clock stretching. This can happen, for instance, when the slave needs more time to fetch or store data. Clock stretching is done by the slave pulling the SCL line low. When the slave becomes available again, it releases SCL and the master can continue. Clock stretching is an excellent source of bus problems when a slave gets stuck or breaks and never releases the SCL line. Remember, the I²C bus heavily relies on the open drain outputs and its pull-up resistors. If these are absent or their value is too high, the bus won't work. If their value is too low, the bus won't work either. There is no recommended value, as it depends on the total capacity hanging on the bus and the required bus speed. There are calculators online that can help you out. I tend to use 10 kilo-ohm pull-ups, which works fine on 100 kHz and doesn't interfere too much with other pull-ups hiding in the system. Note that the pull-up resistors also have an influence on the power consumption of the bus. If the bus is very busy all the time, this will be noticeable and may pose a problem for low-power applications. Switching to SPI or UART or something else may be better in that case. There exist some variations on the I²C bus. TWI, the two-wire interface for microchip, is simply I²C with a different name. There may be some small differences, but basically they are the same thing. SM-bus and PM-bus are simplified versions of I²C intended for system management. PM-bus, for instance, is for power supplies. These buses are I²C compatible, but add error checking frames, something that is missing from I²C. I²C, which stands for Improved Inter-Integrated Circuit, is a recent evolution of I²C. Its goal is to overcome the limitations of I²C while keeping full backward compatibility. I²C is faster, has dynamic addressing, and adds hot join. This allows devices to jump on a running bus. In I²C, the SCL line is no longer open drain but push-pull. This allows adding interrupt conditions and improves the power efficiency. However, it breaks clock stretching, so devices relying on that feature will not work on an I²C bus. History has shown many times how full backward compatibility requirements usually turn into kludges and way too much annoying overhead later on, so let's hope that I²C, I made that up, will be designed from the ground up. Finally, I²S is not related to I²C at all, it is just another serial communication scheme with a confusing name. This brings us to the end of this presentation. I could easily have made it 4 times as long while still not including everything there is to say about the topics I did treat. There are many topics that I did not treat. This slide lists a few of them. These are other serial communication technologies of varying complexity. Even though I didn't mention them, with the information presented before, you should be able to understand them more easily, as they all use similar techniques and principles. Okay, we are back. I hope at least I can see myself. There's Brian also. So that was the end of the presentation. We will now
Before we go into the Q&A, just a reminder that we have a survey running. So if you guys can go to the survey and answer these questions, and then we'll have a look at the results after the Q&A.
Yes, I forgot about that one. Also, so the presentation was 30 minutes, but it's still short and went fast anyway. So if you missed something, don't worry. You can watch the recording later on YouTube. And before we enter the Q&A session, we have the giveaway of this book. And to join the giveaway, you must enter the word embedded in the form that is, if you click on the button on the top of the screen, there you can join the giveaway. So Embedded in Embedded by Jason Long, a really excellent book on embedded programming. Highly recommended. So Brian, did you want to say something before we continue?
Well, that was a common question. What is the code word for entry? And you have answered that. So good luck to anyone wanting to win Embedded in Embedded by Jason Long.
Yes, just type in the word embedded. That is embedded in embedded to get embedded. So then we can move on to the Q&A Q&A session. I will activate it here.
Yeah, Glenn asked, will the presentation be available for download? And as you said, yes, indeed. And if you want a shortcut to our YouTube channel, it is elektor.tv, and you'll find it there. In fact, it's live right now, but it will, of course, be recorded and available for you all.
Exactly. Okay, another question.
This will be up your alley, Clemens. What kind of distance can we achieve between RS485 and SPI bus? I imagine SPI is a lot lower.
Yeah, the SPI you are talking about the centimeters, whereas in RS485 you can go up to kilometers. So that's quite a difference between the two. RS485 is used a lot in industry, things like that.
Yeah, and Andreas had a question about RS485 as well. What can you tell us about termination on these buses?
Yes, indeed. On RS485, you need the termination resistors, like on the CAN bus, and there are some other buses. This is still valid, so don't forget them.
What other questions do we have? Do you need hardware for that book?
Where are the questions? I don't see the questions.
Are you aware if there's any hardware covered in the book?
No, the book doesn't need hardware. The book is valid for any ARM Cortex M device, more or less. No, not all the M's, but the M up to M3. And there is a board that the book uses for examples, but it is not. You don't need the board to understand the book.
So it's not a requirement. Okay. And then a question from Ramiro Suarez. The speed improvement along new serial technologies, is it inherent to the materials, the hardware, the wiring, I would imagine, the cables, or to the coding?
Well, it's sort of both. Sorry. The methods change. To go faster, the serial buses tend to go to differential signaling and with line termination, etc., which becomes necessary when you want to go really fast. It becomes almost a radio, doing radio on wires. So as that gets better, we can go faster. Also because of the processors themselves are faster all the time. And because they are faster, the coding improves also. And so the drivers are faster as well.
Okay, and then a question from Matthias. In RS-232, there are many other control signals such as DTR, RTS, etc. They're not strictly necessary, are they, Clemens?
No, they back to the time when RS-232 was used with a real terminal. So you had a sort of a computer doing only RS-232, and like DTR, data terminal ready and request to send and things like that are signals to set up the communication between the terminals. Today, actually, we use DTR and RTS mostly to reset microcontrollers for to put them in programming mode. So all these other signals you hardly ever use. I don't think, maybe once in my career I had to connect RTS to CTS and nothing else. And often you just looked RTS to CTS directly on the connector. So these are really the signals from the 60s, sort of.
Yeah, I remember modems, for example, were connected with straight through cables. You had data terminal equipment. And later on, when you wanted to switch, send data between two computers, you had to swap over the RX and TX lines, which did complicate things a bit.
The null modem.
Yeah, exactly. I forgot that term, actually. Do you remember sending signals via parallel port using 4 bits at a time with a special kind of cable whose name, again, I've forgotten?
Yeah, there was a program for that, yeah. I remember I did that too. It was the fast way to transfer data between two computers at the time.
Yeah, I still have that cable that I made myself. I can't remember what it was called though.
Sort of like LPT link.
Oliver
why
wants
is this
to know
my
why you...
preferred baud rate? Yeah, well, because it is. You have to have one. I don't like 9600. It's so slow, and this one works usually. Without going too fast, because if you go faster, then you can run into signal quality problems, etc. And this always seems to work for me.
Yeah, although 9.6 used to be fast back in the day, but 150.
Yes, well, yes, it was, but I mean, you have a lot of 4800 on the NMEA things, but that doesn't make my preferred baud rate.
Yeah. There's a question from Richard. Do you know of a comparison selection guide or app that suggests the most appropriate protocol for certain applications? I can imagine like I²C is inter IC, whereas RS-232 is when you want to go a little bit further distance.
Yes, I don't know of a selection guide, or that's why I structured this presentation this way. You write down your specifications, and then you compare to the serial protocol that can do it, and then you find one that will be the best fit.
This is maybe slightly off topic for the presentation, but Shyam wants to know what are the typical improvements in I²C?
I³, yeah, I call it triple. I don't really know how to pronounce the 3 in there. The typical improvements, well, like I said, one is the dynamic addressing, which means that instead of having devices that have a hard-coded address inside, it's the master that can distribute addresses, like a sort of a DHCP system on an internet TCP/IP network. So that is, it makes the network much more flexible. I'm not a specialist in I³ or CCC, but the clock signal, which has become a push-pull, that helps limiting the power consumption on the bus, which is a big improvement, because with the low pull-ups on an I²C bus, the currents are in the milliamps, which is a lot for today's low power systems. Yeah, like I mentioned, hot joining, the jumping on a running bus means plug and play things become possible. It makes it all much more complicated. So in the future, it will be, I think, a big mess. That's about. There are more things. You can consult the internet for all the details if you want to know more.
Yes, indeed, the good old internet, or ChatGPT.
Yeah, well, the ChatGPT only goes up to last 2021, so this is newer.
Yeah. Okay. Question here: can I²C bus problem stall the master device? I remember. Yes. Yeah, carry on.
No, you can continue your.
Well, I remember you would have no problems with, say, RS-232 on your computer, but for some reason, when USB came out, my goodness, sometimes the computer wouldn't even boot if there was a problem on one of the USB devices.
Yeah, that's on I²C. It's similar, like I explained about the SCL clock signal. It's if you pull it low, then the master stops working. So if something goes wrong with the SCL signal, the I²C bus stops working. But the master can also get stuck on other things if the driver alone can mess up. There are all sort of error conditions possible. So the I²C bus is a more complicated bus to get running and to keep running, because it has more features. But because of these features, it is also more flexible. So it's always a compromise between how much trouble you can handle, you want to handle, and how much money you want to spend on it.
Yeah, as always, there's that compromise.
Yeah.
From Martin, can you say a little bit more about the one-wire interface?
Yes. So the one-wire interface, it's used a lot in the Elektor kind of world because of these temperature sensors. But for the rest, it is a more or less obscure thing. It is from Maxim, now Analog Devices. They use it mainly in their I-button things. So it's a one-wire. There's only one wire. And then it works with timeouts. So the master pulls it low, I think, to get the attention of the slave. And then you have all sorts of timeouts. And then both can toggle the line and try to get the information through. It is
basically it's asynchronous.
Well, there is no clock. Yeah, well, the clock is virtual because the time delays are defined, are well defined. You cannot treat them as you like. So there's a sort of virtual clock. So that makes it sort of synchronous. But it is a network kind of system. So you can connect multiple devices all on the same wire. Then every device has an address, and then the master can select by sending its address, select one of the devices and then communicate with it. But in our world, more or less, there is only this DS, what is it again, 1812 or no, 1820 temperature sensor. So
exactly. That's why Theo
yeah, Dallas, that's right.
It was from Dallas.
Dallas then became Maxim and then became Analog Devices. So it is a driver. It's a bus that requires a complicated driver just to read the temperature sensor. And now this temperature sensor is a nice sensor, so everybody uses it. But there are other nice sensors, and which may be preferable, so you can get rid of the one-wire bus altogether.
Yeah, Dallas was quite ahead of their time on that.
Yeah, they break through. Well, it can be multi-drop. Can you give some detail about how this is working? Yeah, well, multi-drop means that you can drop off at multiple places. So it's on a UART bus, when you are sending, you can have multiple listeners. Everybody can connect to the TX line and read the data that's going on. But you cannot send back. Only one device can be connected to the RX line, because otherwise there would be a conflict. So there is only one device on, it's not a bus, really. There's only one device that is allowed to talk back. So there is no real possibility to communicate with multiple devices unless you implement some sort of line sharing, which takes you to RS422. So this, which is why RS422 or 485, I don't remember which one it was, 485, I think, was developed. So UART is not a bus.
Yeah. Okay, then can I²C be used over longer distances? Now, I'm not sure what longer distances means. At low speed, 100 kilohertz is pretty fast to me for that bus, but what sort of distances can you get with, say, twisted pairs or shielded cable?
Yeah, well, you can only find out by trying. I²C, when you change the distance and add more cable to the bus, you add more capacity, and so you have to adjust the pull-up resistors. So it depends on how long the cable is. You can try, I mean, 100 kilohertz is not that fast. If you use, but then again, the voltages are low, so you can do that on I²C. You can level shift the voltage, the high level, up to much more, and then use long wires and see how much you get out of it at the end. Of course, your edges will become less well defined. So it was not intended to do this, and if you really want to do this, then you are on your own and you have to experiment a lot. But think about the pull-ups; they will become important.
Yeah, I mean the clue is in the name. I²C is integrated circuit. So although it's intended to communicate between one IC and another IC on a board, I do remember, I think, seeing some Philips hi-fis in the 90s that had 4-pin mini-DIN that could send the I²C between components of the hi-fi, which was a bit strange.
Yes, sure, but then the distance remained relatively short, like 1 meter.
That's an interesting question from Robert. Sorry, I clicked on the wrong question.
It is from Robert.
Is it not wise to use synchronous transfer over longer cables because of the glitch sensitivity?
Well, the problem of synchronous transfer is that you need two. You need a clock wire and a data wire. And often with long wires, you don't want long cables. You don't want a lot of conductors. So no, the best way for long cables is going differential.
Okay, when I said I clicked on the wrong one, I meant to click on Frank's question first, but Robert arrived just at that moment. Frank wants to know if there's some sort of thing like, instead of binary, trinary or ternary, where you can have more than 1 bit per clock, so multiple voltage levels. That's an interesting one.
Well, that's called a parallel bus, actually.
But on one line, would you have like a 0, a 1, and a 2, perhaps? I've never seen anything like that.
Well, of course you can do that. I don't know if there is an official standard. It's not a If it is, there's not a popular standard, not one that I know of, but of course you can make a bus analog and you can have as many levels as you like. It just makes it more complicated.
And Ari answered that question now with the new single pair Ethernet. Interesting. Shall we have a look at how the survey is doing?
Oh, yes.
Well, it looks like most of the viewers are somewhat familiar with these protocols. I guess I would fall into that category as well. I haven't used all of them, but as I said, I have bit-banged I²C on parallel port, and I've done serial and RS-232, not SPI as much. But you've done them all, right, Clemens?
Yes, and others. I mean, there are a lot of protocols that look like SPI. A lot of manufacturers have at some point implemented some sort of interface that looked a bit like SPI. But yeah, the I²C is actually the most. I've done a lot of serial, of course. I²C is I think it's really now coming up with all these sensors that have I²C interfaces. And then I think it's easier to use I²C than SPI.
Yeah, fewer lines as well. I've seen a couple of people mention I²C here. Is there even such a thing? We've just
no, I made that up. That's what I said in the presentation.
Okay.
I wondered how you would pronounce it, the 4 in I²C.
Yeah, quadruple C.
I²C or I4C. I foresee that it will not happen.
Okay, it looks like a lot of people are happy with the answers. Some people are leaving. Thank you very much for joining us. Should we say a bit about...
I had another slide for the end, maybe.
Yeah, that one.
No, not that one.
End of file.
Yeah, this is end of file, but that was not the... I wanted this slide. Just to show the Elektor products, magazine and links. Let me see. Oh yeah, the next webinar that I know of course, is about the graphics programming on Linux with the Ensemble Graphics Toolkit from Microchip. That one is scheduled for June 22, so hopefully you will be there again. And then again, once more, this webinar has been recorded and will be available on YouTube.
And I think we should say something about our submission page.
Yes.
I'll drop the link in the chat. It doesn't come up elsewhere. But a lot of you are asking how to write for Elektor magazine, and we're always on the lookout for interesting content and interesting submissions. So if you go to elektormagazine.com/elektor-submission-page, and you have some interesting topics, or you know someone and you have a project you'd like to tell us about, please go by there and have a look at our newly created submission page and tell us what you have on offer, because as I said, we're always on the lookout for new information and great projects.
Yeah, so projects you can post, of course, at the Elektor Labs website. If you do that, then they will end up automatically on the desk of the editorial team for where they will be evaluated and see if they are fit for publication in the magazine.
Great. We look forward to seeing some submissions. We had so many participants today, so hopefully there will be some interesting stuff streaming in.
Yeah.
It's a great presentation, Clemens, and it's clear from all the comments. People enjoyed the presentation, so thank you for that.
You're welcome. Yeah, well, that's all for me. I don't know if you something.
That's all from me as well. Once again, thank you for that. I learned something from this presentation, and I think a lot of other people did. Thank you, everyone, for joining us, and enjoy the rest of your evening, morning, whatever it is, wherever you are in the world.
And yeah, hopefully see you next time at the next webinar. Okay, goodbye.
Great. Cheers.